audible, students? I hope I'm audible. Am I audible? Please write down yes if you can hear me in the chat box. Okay. Okay, fine. Okay, so last class we have done up to this numerical and we have found out what? We have found out the settling velocity. Okay, so we have got the formulas for three different formulas for your settling velocity. So as I already mentioned while explaining your plain sedimentation, that we have sedimentation tanks. Okay, so in your sedimentation tanks, those these processes of plain sedimentation is happening. Okay, so plain sedimentation tank, just no need to write notes about sedimentation tank. Okay, just remember that here your all the process of sedimentation that we have read last class, that the settling velocity, the particle whose specific gravity is greater than 1 that of water, so those particles they settle down in a sedimentation tank. Okay, so sedimentation tank, it is generally, it looks like this one. This one is a, this is a rectangular sedimentation tank you can see here. Okay, and this is a circular sedimentation tank. Okay, so sedimentation tank also, we have two types of sedimentation tank. One is your horizontal flow tank and the second one is your vertical or upflow tank. Okay, so you can read about these types of tanks. Okay, uh, you can read it. I don't have the notes right now with me. So basically, I will go to the design problems. Okay, the design of not design, actually some numericals related to your sedimentation tank. Okay, so okay, if you have copy with you, you can please you can write it down whatever I tell. Now let us see some design concepts. Okay, how to design a sedimentation tank. What are the some values we should know about, some values and all. So let us see. It's written here. You see here. See, in sedimentation tank, we use a term called overflow velocity or overflow rate or surface overflow rate. Okay, which is symbolized by V naught. Okay, so it is what is overflow rate, let us see. So it is written that it is that flow velocity at which the tank is designed to operate. Okay, the velocity at which the tank is designed to operate is known as your overflow velocity. So it is again written, mm, just wait. Okay, you see here, from here, in the design, the particles fall downward and the water rises vertically. Okay, from here you see. Okay, let us understand the concept that in this design, that means in the design of your tank, the particles fall downward and the water rises vertically upward. Okay, so the rate at which the particle is settling is Vs, that already we have learned. Okay, and the velocity of the liquid rising is V naught. So it is told that when the particles whose specific gravity is greater than water, those particles when they fall downward, okay, when they settle downward, so that the downward velocity, okay, that settling velocity, it is that is symbolized by Vs, okay. And when the particles they fall downward, what happens? The water, it rises vertically upward. Okay, so that vertically rising up water, it is denoted by your V naught. Okay, the velocity at which the water is rising upward, it is designated by V naught, that is your overflow rate. Okay, that is your overflow rate. So it is written here again. Evidently, if the particle is to be removed from the bottom of the tank and not go out in the clarified water, then the particle settling velocity must be greater than the liquid rise velocity V naught. So obviously, we are trying to remove the particles. Okay, we are trying to remove the impurities that settle at the bottom of the tank. Okay, so what is the condition so that the impurities they get removed from the bottom of the tank is that the settling velocity, okay, it must be greater than the overflow rate or the liquid rising velocity, that is V naught. Okay, only then the the impurities or the settling particles they will be removed. So in other words, it's written here, in other words, Vs should be equal or greater than V naught. If this happens, when Vs is greater than V naught, then one would expect 100% removal of particles. Okay. So, and if your settling velocity it is less than your overflow rate, one would expect 0% removal. That means if your overflow rate it is less than your settling velocity, then you cannot expect the impurities to get removed. Okay, so the condition, you can remember the condition. Okay, the important is a condition is this one. If your Vs is greater than or equal to V naught, then your 100% removal of particles can be expected. Okay, now you need to write down, please write down some formulas. Okay, I will mark the formulas and you go on writing. After that we will solve for numerical, then it will be easy for you to look after the formulas that you have written in your copy. Okay, after looking you can do the numerical. Okay, so you write down um, the overflow rate formula. You write down this one. Okay, overflow rate formula you write down. V naught formula, or or you can say this is your, the other name is your surface loading rate. Okay, also known as your surface loading rate or overflow rate, denoted by V naught. The formula is discharge per surface area. Discharge by surface area. Discharge we can write as your volume by time. Okay, we can write as volume by time by surface area. So ultimately the formula is depth by time. You see, volume also we can write as surface area into depth. Okay, area into depth will be your volume. So finally your V naught formula comes to be depth by time. Okay, you write down this whole thing. I hope you have written. Okay, so let's go to the next formula. This one will be your number one. Okay,
ये क्या हो रहा है भगवान? यामा तुम क्या कर रहे हैं? मत करो।
Richa, please mute your mic.
ये क्या हो गया?
Okay, so the next formula you write down. The next formula you write down is this one. Flow velocity formula you write down. Flow velocity V, small v, you write down V is equal to Q by dH, where B is your width of the tank and H is your depth of the water in the tank. Richa, can you hear me? Richa, can you please mute your mic? Okay, so you have written this. Then next you write down. Next you write down this line. This black color line you write down in your copy. From here to here. Normally, adopted values of overflow rates vary between when, suppose in your question, the overflow rates is not mentioned, so you need to, you can assume, yeah, you can assume some values. So those values it's already mentioned for your design purpose. So you write down normally adopted values of overflow rates vary between 12 to 18 meter cube per day per meter square of plan area for plain sedimentation tanks and between 24 to 30 meter cube per day per meter square of plan area for sedimentation tanks using coagulants as aids. Okay, you please write down this sentence. Later you will get to know what are all these when you solve your numerical problem. Done. Okay. So next, you write down this line, the line that is marked by pen, you can see. Usually, usual values of depth ranges between 3 to 4.5 meter with 1.8 meter as minimum and 6 meter as maximum. That this is the depth of your, talking about the depth of your water tank. Okay, for a sedimentation tank, what is the depth? Where you need to, sometimes you might need to assume the values. So the depth ranges from 3 to 4.5 and your minimum height it can be 1.8 meter and the 6 meter is the your maximum depth. Okay, so you write down this line, usual values from here to here you write down. I hope you have written. Okay, then next you write down this formula. Detention period formula you write down. Detention time we have already explained in the last class. We have learned the time that is required to the particle to settle down, or else if there is no outflow in the sedimentation tank, so the average time that the water needs to fill up the tank is your detention time. Okay, so you write down the formulas for a detention time for a rectangular tank and also a circular tank. Both you write down. Detention time for a rectangular tank and detention time for a circular tank formula you write down. Also, if you complete writing that one, you write down this line. The detention time usually ranges between 4 to 8 hours for plain sedimentation and from 2 to 4 hours when coagulants are used. To write up to here. Okay, not up to there. You can continue. You can write in short form. Okay, no need to write the whole sentence. You can just write that detention period. Give a dash 4 to 8 hours. In bracket, you write for the plain sedimentation, and again detention time dash 2 to 4 hours. In bracket, you can write when coagulants are used. Okay. So, then you write down first this formulas quickly. Okay. I hope you have written the formulas. So now you write down from here, from here to the width. Also, you can write the width. The width of the tank is normally kept equal to 10 meter and not allowed to exceed 12 meter or so. Then the length of the tank, you continue to write from here. Okay, you can write from here in short form. You can write down. So the width also you can write that it is between your this is the width also it is your 10 meter. Okay, it should be kept to 10 meter and it should not exceed. Okay, it should not exceed what, 12 meter. It should not exceed 12 meter. Then the length of the tank is not generally allowed to exceed 4 times the width. Okay, though it may vary from 1 to 6 times its width. So the length, it is generally not allowed to exceed. It is not allowed to exceed 4 times the width. 4 times the width. Okay, and though it may vary from 1 to 6 times the width. 1 to 6 times, you can write it short form like this. Okay, the width, L is equal to 1 to 6 times of B. That means it might be 1B also, 2B also, 3B also, like this, up to 6B it can vary. Okay, 6 times of the width. So next is your the cross sectional area. Okay, the cross sectional area of the sedimentation tank is such as to provide a horizontal flow velocity ranging between 0.15 to 0.9 meter per minute. You write down again, normally kept at about 0.3 meter per minute. Okay, you write down this in short. Please write down, don't write the full sentence. These values you just need to remember for your numerical purpose. Okay, no need to memorize, just you need to remember the values. Okay, so you can write down in short form. So the cross sectional area of the sedimentation tank, it should be between your 0.15 to 0.9 meter per minute, and it should normally be kept at about 0.3 meter per minute. Okay, and the total amount of flow, uh, this line is not required. You write up to this line, then write down quickly. Okay, I hope you all have written. Okay, so uh, next let us directly go to one of your question. Let's see if we can complete. Okay, so this is your question. You see, this is your question. The maximum daily demand at a water purification plant has been estimated as 12 million liters per day. Design the dimensions of a suitable sedimentation tank for the raw supplies, assuming a detention period of 6 hours and the velocity flow as 20 centimeter per minute. So we need to design the dimensions of a sedimentation tank. So that means we need to know the length, breadth, and height of the tank. Then that means the dimensions of a sedimentation tank. So we need to find out the length, width, and height. Okay. So let's see how we can start our problem. It is given that detention period of 6 hours is given. Okay, and we have the daily demand. Okay, the daily demand we have as your 12 million liters per day. Here, so now we can find out the capacity easily. Okay, so you can write the solutions like this. Quantity of water to be treated in 24 hours. Since your the capacity is given, sorry, not the capacity, the maximum daily demand is given in per day. So we need to, and since the detention period is in hours, okay, so we need to convert your 12 million liters per day to hour. Okay, first we need to convert to hour, and then we need to, if you multiply with the detention period, then you will get the capacity. Okay, capacity, or you can say the quantity. So the quantity here, you can directly start from here also. Quantity of water to be treated during the detention period of 6 hours is your 12 million liters. 12 million is your 12 into 10 to the power 6. Okay, we have divided it by 24 since it is per day, and we need to convert it to hours. So it is your by 24 into multiplied by your 6, that is your detention period, and you get your capacity as 3 into 10 to the power 6 liters. Okay, then again your if we convert it to cubic meter, or you can say meter cube, then it will be your this is your 10 to the power 3 cubic meters. So it will be your 3000 cubic meter. Okay, they are converting it to meter cube. Okay, so the capacity of the tank required is your 3000 cubic meter. Okay, so multiply the MDD, that is your maximum daily demand, with your detention period. You will get your capacity of the tank. Okay, the required capacity of the tank. Now, what is else is given? The else given is your velocity of flow as 20 centimeter per minute. The velocity of flow it is given. Okay, velocity is given as 20 centimeters, so we need to convert it to meter, since the previous answer we have converted to meter. So this also, if we convert 20 centimeter to meter, we will get 0.2 meter per minute. Okay, now we can find easily the length of the tank. Okay, so how to find the length of the tank required? It is your velocity into your detention period. Okay, so velocity into detention period, what's the unit? You can meter per second into second. Then if you divide second, it will get cancelled and meter will be left. So your length of the tank is your velocity into it. You can remember these formulas also. Okay, if it is not written previously, you can write it down at the side of your copy. Okay, you can write it side of your copy, then later doing other numericals it will be easy for you. Okay, if you directly remember the formula. So length of the tank formula is your velocity of flow into detention period. Okay. So you got velocity, we already have 0.2, and detention period we have 6 into 60, means converting it to seconds. Okay. Hours to seconds they are converting. So it is 6 into 60 and you are getting 72 meter. Okay. The length of the tank you are getting to 72 meter. Next, you see cross-sectional area they are finding. Cross-sectional area of the tank required is, the formula is capacity of the tank divided by length of the tank. Okay, capacity we already got 3000, length also we got 72. So the answer is your 41.7 meters square. Clear? Now, assuming the depth, water depth in the tank as 4 meter. So we have already learned that the height of the water tank of a sedimentation tank, it is between what? 1 point something to what? 8 meter or 6 meter it is given, right? What was that? You see, the length it is already given as, okay, 3 meter, 3 meter to 4.5 meter can be the depth. Okay, water depth. So they are taking it to be 4 meter. Also, since it is a design problem, so it depends upon you whether you are taking 4 meter or you are taking 4.3 meter. Okay, but that range it should be between your the above mentioned depths. Okay, that is already mentioned in your design concept, so it should be between that. Okay, if you use here to be 3.8 also, then also correct, it will not be wrong. Okay, so they are taking 4 meter, so the width they are finding it to be 41.7, that is your area divided by your depth. Okay, area divided by your depth, if you do, then you will get the required width of the tank. Now you have got the width. Now we have the depth also, we have assumed it is as 4 meter. But one thing in your sedimentation tank or whatever water tank it is, we always provide a freeboard. Okay, I don't know you have heard this word before or not, but the freeboard, I think you have heard, you may heard in fluid mechanics. Okay, so a freeboard is a spacing. Okay, a spacing you can say above the water level. A spacing is given for some safety purposes. Okay, so a freeboard is always maintained above your water level and below the slab of your this water tank. A freeboard of 0.5 meter is always maintained So you need to add the while designing, you need to add the depth of the water tank plus the freeboard. Okay, you always need to add both 0.5 here as a freeboard, and 4 meter is your depth of the tank. So you add both, and the total, the overall depth will be your addition of your freeboard and your water uh, depth, water depth. Okay, so this will be your overall depth. So finally we got our overall, the depth we got. Okay, the width we got, then length also we got as your the what length we got, 72 meter. Okay, we got the length as 72 meter, 10.5 is your width, and 4.5 is your total depth. Okay, so your problem is solved. Okay, so you later you write down, uh, if you want to write it down today, so you can take a screenshot and you write down in your copy. Take a screenshot and write it down today itself. Okay, don't forget to write it down today, otherwise later you will forget. You write it down today. Always do your daily classes notes daily. Okay, don't keep it for later. Okay, you take a screenshot of this, then you take a screenshot of this. I will take your attendance. Roll number 69, 51.
Ma'am.
Okay. Then between 52 to 60, who
Ma'am,
is present?
69.
69 present.
Ma'am,
Okay.
16 present.
Okay. Then 52, 52 to 60, who is present?
53, ma'am.
53 present. Okay. Then 53 present. Then
59. 59 is present, ma'am.
59. Okay. Osborne. Okay. Then 60. No. Okay. 61.
Present, ma'am.
62.
Present, ma'am.
63.
Yes, ma'am.
64, 65, 66.
66.
Okay, 67.
Present, ma'am.
Okay, 68.
Present, ma'am.
70.
Present, ma'am. 70%.
Okay, 71.
Present.
72.
I'm 68%.
68 present. Yeah, given. 72.
Present, ma'am.
Okay, 73. 73. 74.
Present, ma'am.
75.
Present, ma'am.
76.
Present, ma'am.
77.
Present, ma'am.
78.
Yes, ma'am.
79. 80. 81.
Present, ma'am.
82. 83.
Present, ma'am. 83.
Okay, 84. 85. 86.
Ma'am, 84.
84.
Ma'am,
85.
present.
86. 85 is present. Okay. 86 is present. Likha. No. 87.
Yes, ma'am.
88.
Yes, ma'am.
89. 90.
Present, ma'am.
91.
Yes, ma'am.
92.
Present, ma'am.
92 present. Okay. 93.
Yes, ma'am.
Yes, ma'am. 93.
Okay. 94.
Present, ma'am.
95.
Present.
96. 97.
Present, ma'am. 97.
97. 98. 99.
Yes.
Okay. 9900.
Yes, ma'am.
101.